Okay, welcome back, Ling 441. Today we're going to talk about automatic pitch tracking. Having already kind of learned how digital signal processing works, we can take it to the next step or the next level and try to understand how we get a representation like this out of prod. So this is a token that we've heard before.
Yeah, the thing is that if you only met him for a day, you would think he was totally normal.
So this is the spectrogram in the background, and the blue line gives us a representation of what Prot thinks the fundamental frequency of the speaker's voice is at each point in time during this utterance. And that representation is also known as a pitch track. And if we listen to it again, you can get a sense of how when it's higher, the speaker's voice is higher, and when it's lower, the speaker's voice sounds like it has a lower pitch, right?
Yeah, the thing is that if you only met him for a day, you would think he was totally normal.
So on and so forth, right? Okay, so how do we do that? How can we get that sort of information out of a sound file? So we'll figure that out today in basic terms. And where we're going to have to start with this is by thinking about what happens when you voice speech. So with voicing, again, it's sort of like last time I talked about the bilabial trills where you're forcing air out through your lips and then they come back closed because of the Bernoulli effect. We're doing the same sort of thing with voicing, except we have our vocal folds, which are held together. We push out air from our lungs. They pop open due to the air pressure difference between the subglottal region and the supraglottal region of your vocal tract. And then because air flows through them so rapidly, they're going to close again due to the Bernoulli effect. And then that whole cycle will repeat again, except with voicing, it tends to happen a lot more quickly than it does with bilabial trills because of just the physical parameters of the different materials involved or different forces involved, as it were. So each cycle, when those vocal folds pop open, we're going to get an acoustic shock wave traveling through the vocal tract. We learned in 341 that will resonate at specific frequencies in the vocal tract too. We don't really have to care about that so much at the moment, but just keep in mind that's going to form a complex wave. So there will be this repetitive pattern of the vocal folds opening and closing, and then because of the resonance, it's going to look pretty complex. It's not going to look like a nice sine wave like we saw in the previous lecture. What we're going to focus on now is the rate at which those vocal folds open and close and try to figure out how we can get that information out of the signal. And remember that what we call that rate is the fundamental frequency, or the F0 of a voiced sound. So this is what it looks like when I just say the same vowel for a extended period of time. Like that. Maybe I should turn this up a little bit. So this is just the waveform, and you can see maybe that's too loud. There are these spikes going throughout the entire waveform. Those are those acoustic shock waves that you get when the vocal folds open due to the pressure bursting through them, as it were. And we can zoom in a little more closely on these to see these spikes. And we know that sometimes we call them voicing bars. You can also call them glottal pulses. But the big ones are the ones we kind of care about because they're kind of the most obvious landmark that you can latch onto and trying to figure out how often this cycle is going to repeat. This is me doing the same vowel with creaky voice. And because I'm doing that at such a low frequency, a low F0, you can start to kind of get a sense of what the individual glottal pulses sound like. Just strung out in a row. I'm going to zoom in even closer, and this is just a very fine time scale for this waveform. This is what it looks like, the exact same tokens we've been hearing in the last two slides. This, like I said, is a complex wave. You can see the biggest spikes or the glottal pulses up here at the top. They go higher, but after each pulse we get this complex stuff, which does not really look like a sine wave, but you can see is repetitive, right? It's repeating the same pattern over and over again. It's just that the way things actually work out due to all the different factors getting involved, even if I'm trying to be steady with like an that voicing pattern is not going to be absolutely perfectly the same every single time. There's always going to be some random variation from one cycle to the next. So you can actually, if you look closely at this, we can look at a few interesting little deviations. So we have our big spike here. That looks mostly similar here. This little valley doesn't go down quite as low here as it did there. We've got this kind of pattern corresponding to that. This guy corresponds to this, but they look a little bit different. over here. We've got one bump here. We've got another bigger bump. There's two little bumps here, so on and so forth, right? There's two bumps here. There's one bump there. It's not perfect, but it's obviously, if we just look at it, pretty close. So how can we measure the fundamental frequency of a complex wave? There's a general way to think about it, which is just like, how would you do this as a human being looking at a waveform like this? And then we want to be able to translate that to what would a computer do, so that we don't have to like look at the waveform on such a fine time scale all the time, which would be extremely time consuming for us. Okay, so the basic idea, we can kind of see these patterns pretty easily. Even though they're not perfect, we can see, well, here's one glottal pulse, here's the next glottal pulse. There's a duration difference between them. There's some amount of time that elapses between those two glottal pulses, and then the cycle begins again. That duration is the fundamental period of this complex wave. That, if I know what the fundamental period is, then I can figure out what the fundamental frequency is, because there's this very straightforward relationship between the two, right? So fundamental frequency is 1 over the period. If I had, say, a period of 0.01 seconds, or 1/100th of a second for my fundamental period, take the inverse of that, 1 over 0.01 is going to be 100. That would be a 100 hertz fundamental frequency for that particular wave. Usually it's not that simple. I'm giving you the basic example though, so you can kind of see how the principle works, right? We want to just figure out what this duration is, then we can know what the fundamental frequency will be. Okay, so the way we're going to do this, like I said, we're not going to do this by eyeballing it every single time, because we'd have to do that thousands and thousands of times, even for an individual waveform. We're going to have a computer do it, and what the computer is going to do is break up the waveform into individual windows, or what I'm going to sometimes call chunks. So it's going to chop up the waveform into little bits and pieces, and then see how successive chunks match up with each other. And the way it's going to figure out what the period is by looking for the difference in time, how much time passes between the start of some initial chunk and then the start of the next best matching chunk somewhere down the line. So you start at the beginning of your waveform, and then you go down a certain amount of time, and you pick out so beginning of waveform, grab a window, grab some small chunk, move a little bit further down the line, grab an equal sized chunk, and see how well that matches up with what you saw at the beginning. If you get a good match, you say, oh, look, the difference in time between where my initial chunk started and my next chunk began is the period of my complex wave. I'm going to show you that in a lot of detail in a couple of different ways in this lecture. So if you don't get it quite yet, you'll get at least a couple more chances to hopefully understand what I'm talking about. As we get into it, though, you can think about a couple of different parameters we have to worry about when we do this sort of process. So the first is window size, like how much of the waveform do we look at? If my whole waveform is this big, how small chunks do I chop that thing up into? I don't even know if what I said was grammatical, but it sounded good to me. At any rate, the other thing you have to think about is frequency range, like how many different chunks do we compare the initial chunk to? And you can also think about that in terms of like the period range, because these two are basically inversely related to each other. How many different possible periods do we want to look at to find what the actual period of the complex wave is? Okay, so here is this initial waveform, or at least again a chunk of that initial waveform that I was showing you before. We're going to say that time is 0 here where I initially sliced it. And what we want to figure out again is basically what this duration is. How long does it take to repeat itself? If I take an even smaller chunk or a smaller window of this waveform, I could grab, say, just this part of it, and it would look like this in windowed form. Or I could take maybe a larger window that would look like it would be this big. So normally when I teach this in class, this is the point at which somebody will ask, well, why don't you just grab like this part to this part from one glottal pulse to the next? And the trick is that your computer does not know yet where these peaks are. It's just going to grab some indiscriminate amount of time and window the whole waveform up in those bit sizes of windows. So say this is like 10 milliseconds long or something like that. It's going to grab 10 milliseconds here. It's going to grab 10 milliseconds here. It's going to grab 10 milliseconds further down the line, all the way through. And it's not going to look at what the shape of the waveform is. That's too complicated for our purposes right now. We're flying blind here, but eventually we develop vision. It's kind of nice how it works out. Okay, so let's say I grab a window of that second size that I mentioned on this previous slide. So it's going to be about this long. This is time at time 0. I want to figure out what the fundamental frequency is at this point. And so what I'm going to do is go somewhere further down the waveform and grab another chunk of the exact same duration, but starting at some point at where I suspect the fundamental period might potentially be. So let's say I grab a window at this point and it lasts that long. Crucially, these two windows, my initial window and this kind of comparison window, they have to be the same duration so that I can do the math in the right way. But if I grab this part, it's going to look like this. The initial one looked like this, and you can see there's patterns here that look similar. We can see these two big glottal pulses jumping out, but the timing is different, right? So I get a few initial bumps here from this chunk that I don't have in this chunk here. So ultimately, they're probably not going to match up that well. I'm plotted them on top of each other here so you can get a better look at how that matching process would work. Ultimately, we want to see if these line up. We're trying to get the timing right. That's kind of the crucial thing. And we're going to figure out how well the timing works by developing a measure of what's called correlation, how well the two windows match with one another. So specifically, we're going to use a measure called autocorrelation, or at least this process is known as autocorrelation. Auto means self in ancient Greek, and correlation is just two things that relate to one another. We're matching the waveform up with another part of itself. That's why we call it autocorrelation. And the specific measure we use is the point by point or the sample by sample products of the two chunks. That's the point I made before. And I'll walk you through the math here in a second, but what we're going to do, you may have heard this measure called the dot product in the past if you have taken certain math classes in your life, or maybe if you just learned it on the internet or wherever, I don't know. But it's the sum of the point-by-point products of the two waveforms. Okay, so let's say we have window X, like that's our initial window, and then we also have another window Y, another window of the waveform further down the line. Window X has n samples, and window Y must also have n samples. So if window X has 10 samples, window Y has to have 10, so on and so forth. I'm going to give you some examples with, I think, 6 samples on the next slide. So the way the math works is, I'll just give you the notation here. So let's say we're talking about window X. The first sample of window X is X sub 1. The second sample is X sub 2, so on and so forth, until we get to the last one, which we're going to call X sub n, or the nth sample of window X. This is a nice, beautiful little English word that has no vowels in it, at least not the way it's written. Likewise, for the first sample window Y, we're talking about Y sub 1. So when we do this correlation measure, we take X sub 1 and multiply it by Y sub 1, then add it to X sub 2 times Y sub 2, blah, 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 so on and so forth, until we get to X sub n times Y sub n. We take all those products, add them up, and we get this correlation measure, which we're going to call R. The larger R is, the better the correlation between the two windows. So we want to find the sort of two windows that match up best with each other. We want to find the windows that have the largest R at the end of the day, because the computer can only think in terms of numbers. Okay, so like I said, these are some examples, and normally in class I will walk through these on the board. I will write this out just to make sure the math is being digested at the appropriate rate. But let's say I have my initial sample X, or my initial window X. It has 6 samples in it. These are at successive points in time, and this is the amplitude value in each sample. So it starts out here at a relatively high 0.8, then it goes down and bottoms out around here in sample 4, then it bounces back up again for sample 6, so it's kind of, almost like a sine wave like that. For window Y, though, we're starting out in negative territory, then it goes up a little bit by sample 4, and then it goes back down. So this one kind of has a mild peak here in the middle. This one has peaks on either end. If you take the products of these things, the way we're going to do this mathematically is you just do the sample 1 for x times sample 1 for y, 0.8 times negative 0.3. That product is negative 0.24. Likewise, 0.3 times negative 0.1 is negative 0.03, so on and so forth. You can do the math at home if you really want to double check my work. I'd be surprised if you do, but go ahead and do that if it makes you feel more comfortable with this, because at the end, after you get all 6 of these products, what you're going to need to do is add them all up. So negative 0.24 plus negative 0.03, so on and so forth. All of these 6 products are going to add up to negative 0.48. That's the R value for this particular combination of windows. That's negative, and like I said, we want R to be big to give us a good match. So that's doesn't seem to be moving in the right direction if we're in negative territory when we get the dot product for those two. I'll give you another example. So this is the same X as we had before, just so you can see 8.3, negative 0.2, so on and so forth. And then we're going to look at window Z, which maybe is a little further down the line in the waveform. And window Z, like window X, kind of has a peak here at the start, goes down, and then comes back up. It doesn't match up exactly with X, but it's kind of the same overall trend in the numbers. So if we calculate the products of all these, sample by sample matches, 0.8 times 0.7 is 0.56, 0.3 times 0.4 is 0.12, so on and so forth. All these wind up positive, which is nice. And the reason they're winding up positive is because they're all matching in sign, whether it's negative or positive. So when this one's positive, this one's positive. When this one's negative, this one's negative. That gives us a good match overall. And our total sum of products is going to be 1.26. And I'm also going to mention another fact here, which I think I put in the notes. You get a lot of bang for your buck when you get peaks matching up with each other. Even if they're like negative peaks down at the bottom, those will count for more towards the overall product than this kind of middling stuff here where you're near zero. So this is kind of the computer's way of visually identifying those big glottal pulses and trying to match them up. Just got to figure out where they line up in time. Okay, so that's the basics, the kind of grunt work of the mechanics of how this a computer would go about figuring this out. We can go back to this example where we're going to look at it visually, and you can kind of see because these peaks are not matching up and because we get negatives corresponding to positives, so on and so forth, we're not going to get a good correlation between those two. Yeah, so I've got little arrows there just kind of prove that point, but hopefully you can understand that a little more easily now. We're going to say, well, what the computer does, it comes up with a correlation measure for this guy, and then it just moves on. It doesn't say, well, this is good or bad. It just gives me a number. And then it's going to move on to the next window it can choose from at time equals x plus 1, a little bit further down the line, and it's going to go through the same process for this chunk as well. So I've still got the same original chunk. I'm moving a little bit further down the line to this one, and I'm going to calculate R for the combination of these two little waveform chunks. So at this point, we're dealing with a potential period of x plus 1. So x is sort of where our initial sample was, and then we're moving to the next sample down the line. And these are also, they're a little bit closer, but still a little bit off time-wise, right? So that's not perfectly lined up with that or that either. If we move a little bit further down, there's a little stray star here. I will get rid of that. Then we get what looks like it's going to be a better matching chunk. And so we just grab this part, we line them up, see how well they work, and it's pretty good. It's not perfect. That's more of a product of me just not being able to slice them up by hand that well. But at some point, you're going to get two windows where the peaks line up, the valleys line up, and it looks pretty good, and you get a nice big value for R. So we're just going to say that this is the best match in this particular case of our theoretical example. So if that's our best match, if that calculation gives us our highest value for R, then the computer says, well, my period is X, whatever that is, plus 2 samples, and it's this amount of time. And based on that period, I can figure out what the fundamental frequency is by just taking the inverse of that, like that. Yeah, so at this point, I'm going to pause, now that you know the basics of how this works, and just ask you, how many possible periods do you think the algorithm needs to check? We, in this set of examples, looked at 3 different possible periods. One was x, one was x plus 1, one was x plus 2. How many different chunks do we need to take down here to try to figure out what the fundamental frequency of this creature might be? Think about that for a second, and I'll start up again with the answer in another video.